All right, let's finish section 3.3. I'm gonna go over example 4, 5, and 6. After example 4, 5, and 6, I will post the problem for this lesson, kind of similar to the 3 that we are about to see today, okay, together. The first video was a little bit longer than I expected. It was like 53 minutes, but we did go over the asymptotes there. And in this one, we're gonna go over how to find every parts of it, increasing, decreasing, any relative extrema, concave up or down, using first derivative and second derivative, and we'll try to sketch a rational function, okay? All right, so let's start with f of x. We have 4 over x plus 2. So let's go over, let's find these asymptotes very quickly. Where's the vertical asymptote at? Vertical asymptote is at x equals -2. Okay, that's what makes the denominator 0. Horizontal asymptote, because the degree of the denominator is greater than the degree of the numerator, if that's the case, then we have a horizontal asymptote at y equals 0. So we have a horizontal asymptote at y equals 0. And slant asymptote, well, we're not going to have one because in order for you to have a slant asymptote, remember, the numerator's degree has to be exactly 1 greater than the degree of the denominator. So this will be none. So the first 53 minutes that we spent this morning were all about finding these 3 asymptotes. But now we know how to do that. We did it really quickly. Now let's find the intercepts, okay? Because all these little parts that we find here will help us graph a rational function without a graphing calculator. All right, y-intercept is when x is equal to 0, right? So plug in x equals 0 into your function. Y is going to be 4 over 0 plus 2. That's going to be 4 over 2. So we have a y-intercept at 2. So what you will do is you will plot 0, 2 later on your graph, okay? Now let's find the x-intercept. That's when the y value is equal to 0. So set the entire function equal to 0. So say 0 equals 4 over x plus 2. Now let's try to solve this. What you can do is you can multiply both sides by x plus 2, right? What happened to the left side? This will multiply and give you 0. Cancel, cancel, you get 4 on the right side. Uh-oh, will we ever hit x equals 0? Looks like we're not going to. So we have no x-intercept. Not only that, we just proved that we have no x-intercept, we also just show that our graph will never cross the horizontal asymptote of y equals 0 because it's just not going to touch y equals 0. If it's not going to touch y equals 0, how is it going to cross y equals 0? So not only that we just saw that there's no x-intercept, when we graph it, we'll use this idea and make sure that our graph never crosses the horizontal asymptote at y equals 0. Now, A, B, C, they were all pre-calc ideas. Now, let's do some calculus with it. Now, in order for you to find the increasing or decreasing interval, you need to find the first derivative, right? Now, who is the quotient? So you either use the quotient rule if you like quotient rule, but I think this one I can avoid quotient rule. And for me, whenever I can avoid quotient rule, I'd rather do chain rule. So I'm going to rewrite this f of x so that I can use a quotient rule, okay? Not the quotient rule, but the, what's it called? The other rule. The chain rule. So, you know, guys, I paid like $8 for this app. I'm going to use every function of it. All right, I'm going to go ahead and rewrite my f of x. Take a look. This is pretty neat. I can write this as 4 times x plus 2 raised to the what power? Negative first power. I can do that. We can rewrite it. And then we can take the derivative of this f of x. That's going to be 4 times. Leave that 4 alone. But what comes down? That exponent of -1 comes down. So I will need that -1 in front of it. And then the exponent will go down by 1, right? So what's going to be the new exponent? The new exponent will be -2, right? Well, we do need to apply the chain rule. So what is the derivative of the inside part? What's the derivative of x plus 2? That's simply going to be just 1, right? So I really don't need to write the 1 there, but later maybe you will see a case where you have to multiply by the derivative of the inside function. And if it's not something other than 1, you do need that, okay? All right, let's simplify this. F prime of x is then, let me find all my constant. 4 times negative 1 times 1. What's that going to give you? Negative 4. And then I will have x plus 2 raised to the negative second power. We did this like back in the when was it? January or February. So it's been a while. So if you forgot how to use the chain rule, that's what it is. But maybe later I may have to use the quotient rule. But I was able to avoid using the quotient rule by rewriting this rational function as like 4 times x plus 1 to the x plus 2 to the negative first power. But why did I find it? Well, because in order for us to find the increasing and decreasing interval, we need the critical values. So let's find the critical values. Critical value. Now remember, in polynomial cases, that was when this f prime of x, the first derivative was set equal to 0. This will... Can it be equal to 0? Well, let me write it down. The f prime is negative 4 over x plus 2 to the second power. What I just did was I rewrote this part as a denominator, okay? So this will never be equal to 0. We can, and it's similar to what we just showed by trying to find the x-intercept. That will never be equal to 0 because the numerator of this fraction will never be equal to 0. But what was the second case for finding critical values? It's wherever the denominator or the function is undefined. F prime of x is undefined, or it does not exist at what number x equals negative 2. So we have the critical value at negative 2. What we're going to do is check the signs to the right of it, check the signs to the left of it, and that's how we're going to tell the increasing or decreasing value. So here, let's plug in a number that's greater than negative 2. I'm going to plug in 0 into my first derivative. That will be negative 4 times 0 plus 2, negative 4 divided by 0 plus 2 squared. That will be negative 4 divided by 2 squared. I will get negative 4 over positive 4. I know this is a negative number. So what we know is that to the right side of negative 2, this function will be decreasing. Now let's check to the left side of this. Plug in a number that is smaller than negative 2 into your first derivative. So I'm going to plug in negative 3. Negative 4 divided by negative 3 plus 2 squared. What's that going to be? Negative 4 divided by negative 1 squared. That's negative 4 divided by positive 1. And we just got that this is also a negative answer. So this is also decreasing. So we just found out this is a decreasing function, period. It's not increasing anywhere. So I don't know how my math lab will want their answer typed in, because it's not wrong to... I would say it's decreasing everywhere. It's decreasing from negative infinity to positive infinity. But if they're not accepting that answer, if they don't like it, maybe try to break this into negative infinity to 0 and 0 to positive infinity. I didn't really see this, but they should be both okay. Give me 1 second. I may be able to check this out real quick, okay? Where is this decreasing? No, somebody already kind of started this homework, so I can't really... Well, anyways, I know you'll be able to type in different answers, and then, but, you know, for me, they're the same. All right, now let's determine the coordinate of the relative extrema. Now, relative extrema, relative minimum or maximum, will happen if a function is decreasing and then changing it to an increasing, but there's no change here, right? This is an ever decreasing function. So are we going to have any relative extrema? No, none. Because this function is just keep on decreasing. We're not going to have any minimum or maximum here. All right, now let's go down to F. Oh no, we have to find concave up or concave down. Now guess what we're gonna have to find? You need to use the second derivative. But don't be afraid to take derivatives in a calculus class. We can do this. Let me write down the first derivative down here. The first derivative was negative 4 times x plus 2 squared. Oh, to the negative second power. So we'll go straight from there. We're going to take the derivative of this. The second derivative is going to be, well, keep the negative 4 the same, right? But bring down your negative 2. And then go down on that exponent. So negative 2 will now go down to negative 3. And technically do multiply by the derivative of the inside part. Derivative of x plus 2 is 1. What was that? If I multiply this, if I simplify this, I will get f double prime equals this times that. What's that going to give us? Constant, the leading coefficient is positive 8. X plus 2 to the negative third power. If you want to write this as a fraction format, a rational format, you can write this as 8 over x plus 2 to the third power. So we found the second derivative. So on your problem that you're going to submit for me, you need to show me the first derivative and the second derivative. Now, nowhere on this paper I will ask you to find those, but in order for you to find the intervals where the function is increasing, decreasing, or concave up or concave down, you need to find them, okay? All right. Now, possible or potential inflection points is where this function is either f double prime is equal to 0 or f double prime of x does not exist. That's how you find these boundary points, right? So, well, first of all, this function will never be equal to 0 because the numerator is already set to 8. That's just not going to turn into 0, right? So where does it not exist? Well, you can see how the denominator is x plus 2 to the third power. So what we're going to do is we're going to use x equals negative 2. I think, again, didn't we do that? Yeah. So let's check the concavity by plugging in numbers to the second derivative. To the right side, let's plug in 0 because 0 is greater than negative 2. But remember, we're plugging this into the second derivative to find concavity, right? So if I plug in 0 into the second derivative, I will get 8 over 2 cubed. Well, that's going to be positive. So what we know is that to the right side of negative 2, this function is concave up. Now let me plug in a value that is smaller than negative 2. Let me do negative 3. 8 over negative 3 plus 2 cubed. That's going to be 8 over negative 1 cubed. Now what's that going to give you? Well, that's going to be a negative value. So this section to the left of negative 2 will be concave down. So I know you worked with this last week, but that was using polynomial functions. And now this section is you're just working with, I wanted to move this, but it's not moving. This section is where you have to use the rational functions. But the idea is still the same. You have to find that potential inflection point. And now I would say that negative 2 is going to be special. So if they ask you for inflection point, what you're going to do is you're going to plug this into the original function to find the y value. I give up on moving that. So let me do that. Let's plug in negative 2 into the original function, into the original f of x. By the way, I did not write the notation here. I should probably try to do that. Out of room. I'm really out of room. But I think I can squeeze in the answer here. Concave up on negative 2 to infinity. Concave down on negative infinity to negative 2. Okay, so then make sure that you give me your answers also in interval notations, okay? Now, let's plug in negative 2 into f of x so that I can find the y coordinate of this point of inflection. F of x was 4 over x plus 2. So if I plug in negative 2 in here, 4 over negative 2 plus 2. Uh-oh, undefined. This is not going to work because this is 4 over 0. So if they ask you to determine the coordinates of the point of inflection, what should we say? Oh, no point of inflection. I'm sad because the concavity changed. So I wanted to call that a point of inflection, but there is no way for us to plot a point at x equals negative 2. In fact, x equals negative 2 is where we're going to have our vertical asymptote. So we don't have a point of inflection for this function. But let's try to put all this idea together and sketch a nice function for them. Okay? So just graphing my x-axis, y-axis, and that's what you can do too. Just give me an x-axis and y-axis. We do have a vertical asymptote and x equals negative 2. So you do want to plot that, okay? Make sure you give me a dotted vertical line and x equals negative 2. And what was the horizontal asymptote? Horizontal asymptote was at y equals 0, right? So I know it is the x-intercept, but just still try to squeeze in or like draw a dotted line at this x-axis, because that is the horizontal asymptote. Now we did find a y-intercept, didn't we? The y-intercept was at 0, 2. So I'm going to plot 0, 2 here, 1, 2, and plot a point right here. And there was no x-intercept. But what I know is that this graph, as it's trying to go to this vertical asymptote, is going to go up like crazy. And you know, I know this because this function is decreasing everywhere. So as it's going down, as it's going to the right side, I just need to make sure that I go down. But I can't go too far down because didn't we show that this graph will not cross the horizontal asymptote of y equals 0? So it's just going to get really, really, really close to this horizontal asymptote as it's going to the right side. So I know this side of the graph will look like this. This side of the graph will look like this. Wouldn't it be nice to have one more point to the left of it? So why not? Let's plug in a value so that I can just have at least one more point. I'm going to plug in f of maybe negative 3 because this is negative 2. I do want to know where the graph is at y equals negative 3. If I plug in negative 2, I will get 4 over negative 3 plus 2. That's 4 over negative 1. So the y value will be at negative 4. So what I can do is I can plot negative 3, negative 4 on my graph. Negative 3, 1, 2, 3, 4. So I have a point right here. Now, the more points you have, the more accurate your graph will be. But for me, that's enough. Because I know this is going to be decreasing from left to right. It's just going to go down from left to right. So let's go ahead and graph something that's going down from left to right. But make sure this piece is bounded by your asymptotes. So as this graph is approaching my vertical asymptote of x equals negative 2, this is just going to keep on decreasing down. It's not going to be able to cross that vertical asymptote. But as this is, whoopsies. Well, to the left side, it's going to approach your horizontal asymptote of y equals 0, but it's not going to be allowed to cross that horizontal asymptote of y equals 0. And this is just based on everything that we found in part A through G. See, it's possible to graph a rational function without a graphing calculator, but just out of curiosity, how close were we? Let's go ahead and just use Desmos to see this, okay? I'm going to go to Desmos, my graphing app, this one, and then I will graph that. Our function was 4 divided by x plus 2, right? Oopsies. And then, if you just want to graph your asymptotes here too, you can say, hey, graph y equals 0, I may be able to change this to dotted line, red dotted line, and then I'm going to ask them to, hey, graph the vertical asymptote of negative 2, and then I can tell them to, but I want this to be a dotted line, guys. And then I can see the graph. Look, this looks exactly like what we just did by hand, right? We do have a we do have a, what's it called? The y-intercept at y equals 0, 2. And it looks like we do have a point at negative 3, negative 4. Let me see, negative 3, negative 4. We do, we really do. But it's never crossing the horizontal asymptote of y equals 0. So I would say that was a very good problem that we did together. So, please, because you are allowed to use graphing calculator. When you do this classwork problem for me, make sure you graph it to see if your graph matches what you found. But let's do, guys, let's maybe just one more, okay? Because I should try to keep my lesson videos probably like an hour and 15 minutes for each class, but I'm being a little sneaky. You've been watching things that are more than that for a while, but maybe after example 5 I will go ahead and just post, and who knows, can I ask you to try now? That one's going to be a little special. Oh, we'll keep going. I know I'm getting lazy, I feel like. All right, example 5, let's sketch the function, the graph of this function g of x. We have 6x minus 7 over x. We know that we have a vertical asymptote at x equals 0 because that's going to make the denominator 0. Now, horizontal asymptote, since the degree of the numerator, n equals 1, and m, the degree of the denominator, is also equal to 1, we do know that the leading coefficient ratio is simply going to be that horizontal asymptote. So the leading coefficients are 6 and 1. So we have a horizontal asymptote at y equals 6. Now, since the degree of the denominator and the numerator are exactly the same, we're not going to have a slant asymptote. So none for slant asymptote. Let's find the y-intercept. Plug in x equals 0. So the y value, or the y-coordinate of this x-intercept, is going to be 6 times 0 minus 7 over 0. Oh, look, that's going to be negative 7 over 0. This is undefined. So guess what we just found? We have no y-intercept. And I was thinking about it. I was like, why do we not have a y-intercept? I want to have one. But it's because, take a look at the vertical asymptote. X equals 0. That is actually the equation of the y-intercept. So this graph will not cross the y-axis at all. Okay. All right, let's do the y-intercept. Hopefully we have one. I'm going to go ahead and plug in y equals 0, or set the function value equal to 0. 6x minus 7 over x is equal to 0. Multiply both sides by x. Multiply both sides by x. X times 0 is 0. This cancels out. So we'll get 6x minus 7. We can solve this. I think I have a typo because B says determine the y-intercept and C says determine the y-intercept. Please do me a favor. Change this to determine the x-intercept. Okay, whoopsies. Let me see if I had that issue up here. No, I didn't. That one was okay. So this one I just had to change it. Add 7 to both sides. You get 7 equals 6x. That means we have an x-intercept at x equals 7 over 6. So later you will plot 7 over 6, comma, 0 on this graph, okay? Not the nicest point, but it's okay. We can just plot something slightly over 1 and call that 7 over 6. All right, now let's do the calculus piece, guys, okay? Should we try to avoid quotient rule again? You know what? I already kind of avoided my quotient rule above on example 4. So let me do quotient rule this time, okay? So let's quickly write down the quotient rule. Quotient rule. You use that when you're taking the derivative of a quotient, and we usually call it just f over g prime, right? F is the function on the numerator, g is the function in the denominator. Remember, the quotient rule is the denominator is just simply going to be g squared, and the numerator is going to be gf prime minus fg prime. Okay, so that's the quotient rule. Let's list our f and g here, okay? F is equal to, if I can use this room over here, f is equal to 6x minus 7. F prime is equal to 6. G is equal to x, so G prime is equal to 1. Now you got all your pieces listed. Oh, I love this problem. Let's go ahead and find g prime of x by using this quotient rule, okay? Now the denominator will be g squared, so I need my x squared in the bottom, right? All right, let's keep going. The numerator is where we have to just do g f prime, g times f prime, minus f times 6x minus 7 times g prime, which is going to be 1. Nice. It's not going to be that bad at all. So if I simplify this, I will get x squared stays in the denominator, right? But the numerator will be 6x minus 6x plus 7. I hope you're okay with why that's turning into plus, because I'm distributing this negative to these two, okay? All right, what happened to the 6x on the numerator? The 6x will cancel out. So we found that g prime is simply going to be 7 over x squared. Oh, that's not that bad at all. We can work with that. Let me go write that down on part D, okay? So we just found on our little work over there that f prime, I called it f again here. You know, I changed the name of the functions, but never really go back and change the name of the functions in these directions. So if you can please forgive me, and change these to g. Say g prime of x is equal to 7 over x squared. And I wanted to really fit all that work down in this little box, but I knew that I needed a little more room. So I used that room above there to find the derivative. All right. Now, in order for us to find that one boundary point, we will either find where this g prime is. Either this g prime is equal to 0, or where g prime of x does not exist. In order for a rational function to be 0, the numerator has to be 0. The numerator is 7. 7 is never going to be 0. So the first case will not work. The first case is not going to be 0. So what we're going to do is we're going to go with this idea. This g prime of x does not exist. It's undefined when x is equal to 0, right? Because 7 over 0 squared will be undefined. So 0 is the point that you're going to use. That's the only critical value that we have. This is the critical value. Let's plug in a number that's greater than 0, say 1, into our derivative function. That's going to be just positive 7. So I know this section is positive in the derivative sign. So I know this side will be increasing. Because the first derivative came out to be positive, we know this function is increasing to the right side of 0. Now let's plug in a smaller number. I'll do 7 divided by negative 1 squared. That will be 7 over 1 again. So this is again positive. What you know is this function is also increasing to the left side of 0. So if they didn't change, if it's increasing everywhere, there is no relative extrema. So you're going to say none for the problem where it's asking you determine the coordinates of the relative extrema. We don't have one. We can still give them the intervals though, and we should. I always forget. G is increasing on negative infinity to 0 and 0 to positive infinity. Or I guess you can go ahead and just say G is increasing everywhere. We're going to have that vertical asymptote at x equals 0. But, you know, really, this function is increasing everywhere. I'm just not sure which answer my math lab will ask you to do. Because I remember on homework 3.1 and 3.2, they were asking for 2 different ways. So, you know, you try to type these in on your homework this week, okay? All right, let's do the concavity. Now, g prime wasn't too bad at all. G prime was 7 over x squared. So g double prime, I think I can avoid quotient rule and just find the second derivative. I can write this as 7 times x to the negative second power, right? Take the derivative of that. That will be 7 times, bring down the negative 2. Just make that exponent go down by 1. And if you multiply your constants here, your g double prime is going to be negative 14 times x to the negative third power. You can write that as negative 14 over x cubed. Now, this is going to be undefined. G double prime is undefined at what number? X equals 0, right? But this is never going to be equal to 0, but that's still fine. That is a critical, I shouldn't call critical value. This time, this may be our potential point of inflection, okay? So let's go ahead and draw your number line, 0. But this time, you are plugging in a value to the left of 0 into the second derivative, okay? If you want concavity, you want to use the second derivative. So plug in negative 1 or negative 2, any number that's smaller than 0 into your second derivative. That will be negative 14 divided by this number cubed. Well, that will be a negative over negative, right? So comes out to be positive. What I know is that this section is concave up. Now let me plug in a value that is to the right side of 0. What is g double prime of 1? That will be negative 14 over 1 cubed. Negative 14 over positive 1. Well, that's a positive. Oh, whoopsie. What am I saying? That is not positive. Negative divided by positive is negative. So we know to the right side of 0, this graph is concave down. Okay? Let me just write the intervals here. Concave down on 0 to infinity and concave up on negative infinity to 0 because we want to give these intervals an interval notation. Don't forget to do that, okay? All right. But say that now I'm thinking, well, that's my point of inflection right at 0. So let's plug in x equals 0 into g of x. Okay? Now reminder, g of x was, I forgot, 6x minus 7 over x. So if you plug in g of 0, we're going to have an issue, right? This is undefined. Remember, because x equals 0 was our vertical asymptote. So what will you say? If they ask you to find the coordinates of the point of inflection, we're going to say, oh, no point of inflection. I really wanted to call this guy the point of inflection, but since we cannot find the y value, we cannot plot a point on the coordinate plane, right? But that's good enough. That's good enough. Let's graph a function. So x-axis, y-axis. Make sure to plot your vertical asymptote. Vertical asymptote is at x equals 0. So I know it's kind of awkward to draw a vertical line that is on top of a y-axis, but that is my vertical asymptote. Now the horizontal asymptote, I remember it was up at y equals 6. So let's plot that. 1, 2, 3, 4, 5, 6. We're going to have a horizontal asymptote at y equals 6. So the graph will be kind of shifted up, this much. All right, we did not have any y-intercept, but we did have an x-intercept, right? We did have an x-intercept at 7 over 6. So I can plot that this is my 7 over 6. This is my 7 over 6, 0, my x-intercept. Now let's graph this function. This graph is increasing everywhere. So what I know is that this graph, as I'm going to the right side, this is going to go up. But it cannot cross the horizontal asymptote of 6. It cannot cross the horizontal asymptote of 6. And you know what? I'm just saying that, but I should really show it to you why this is not crossing y equals 6 real quick. Take a look. Assume that y value is 6. Assume that y value is 6. What will be the x value that will make this true? Multiply both sides by x. You'll see the left side is 6x. The right side is 6x minus 7. Notice that. If you subtract 6x from both sides, you'll get 0 equals negative 7. Now, this has no solution. What we just did was algebraically showing that this function can never have a y value of y equals 6. So, that's enough for me to know that this will not cross this horizontal asymptote of 6, but it's just going to get really, really close to this y equals 6 as x approaches positive infinity. And I can go to negative infinity as I'm getting really, really close to this vertical asymptote of x equals 0. And you see, this is definitely concave down, right? This is definitely concave down. I can see your little frowny face right there. All right, let's go to the other side of this graph. It will be nice to have at least one point to the left of it. So what I may do is I may just plug in a random value to the left of it. I'm going to plug in -1. What if x is -1? What will be the y value? G of -1 is 6 times -1 minus 7 over -1. So that will be -6 minus 7 over -1. I'm having a moment. So this will be what? -13 over -1. The y value will be at +13. So I have a point at -1, 13. So let me try to plot that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have a point right here. And then I can just kind of put a graph up there. To the left side, I know it's never going to cross this horizontal asymptote. So I'll just get really, really close there. But notice from left to right, this function is increasing, right? And as it's approaching the vertical asymptote, it's just gonna forever increase, but it will never cross the vertical asymptote. So that's the graph of our g of x. And let's just double check this. 6x minus 7 over x. So the function was 6x minus 7 over x, and we know that we have a horizontal asymptote at y equals 6. Let me graph that as a dotted line. And we do have a vertical asymptote at x equals 0. I'm going to just graph that using a dotted line. This is called Desmos, and I like this a lot. You see how this is very similar to what we have graphed. We do have a horizontal, what's it called? Let me go there. We do have a point at 1.167. That must be 7 over 6, 0. So that's our x-intercept. And that one random point that I just found to graph this, we have a point also at, let me see, -1, 13. So that's looking great. And it's concave down to the right side of this graph. And it's concave up to the left side of that 0. And it's increasing everywhere. Notice from left to right, this graph is going up. From left to right, this graph is going up. So definitely check your graph after graphing things by hand.